So, this program shows us how to use the variational principle to compute or to solve the Schrodinger equation for a given potential well. So, remember in the when we talked about the methodology, so towards the end I gave a sort of an assignment to compute this potential well. The eigenvalues and eigenfunctions of the Schrodinger equation when your potential is given by an attractive square well. So, this highlighted part here, so this is the definition of my potential. So, what it means is that the total width of the potential is given by B and it is a symmetric potential centered at the origin. So, from minus B by 2, so this part what this means is from minus B by 2 to plus B by 2 the potential has a value minus V0, and for other parts of the for other values of x the potential has a value 0. So, let us see how we can convert this to a numerical problem to solve the Schrodinger equation. So, what if you remember the methodology which we discussed. So, what we have we need to do is we need to expand our wave functions in a basis, and as a basis we are using the plane waves, and then we need to construct the Hamiltonian, the H matrix, and then we need to diagonalize it. So, for the diagonalization we will be using this particular subroutine called DSYEV. We will see what is there very shortly. This is a part of the LAPACK suite of codes. And another thing is this code is written assuming that everything is in atomic units. What it means is that h bar square by twice m is equal to 1. So, as we have seen for other Fortran codes, so we start with this implicit none, and then in this part, in the first part we do the variable declarations. So, now remember this when we talked about in the numerative method. So, we talked about the importance of the accuracy of my calculations when doing calculations for quantum mechanical problems, and as a result of which, so I need to do everything in double precision, at least in double precision. So, therefore, I am declaring here through this parameter dp, this integer variable, that everything is in double precision. Then in many places I will be needing the value of pi. So, I am setting pi to 3.14 this value, and then I am declaring it as a parameter and a real number. Then I need integers. So, where NPW is the number of plane waves that go into the calculations. So, remember the number of plane waves, so that depends on twice pi by a into n, where n goes from 0 to 0 plus minus 1 plus minus 2 like that to plus minus n. So, this n is that number. So, basically say if you give n in your input. So, this will be my input, and where if I give the value of n, the NPW will be 2n plus 1 in our calculations. So, if I give say the value of n to be 20. So, the number of plane waves that goes into the expansion of my wave functions, that will be 41. Then V0 is the value of the potential, this constant, the depth of my potential well here. A is the periodicity of my plane wave which I am using, and B is the width of the potential. So, this is this same B which is here. Then I have some allocatable arrays here. The first array, this Kn, this stores the k vector corresponding to each plane wave. E stores the eigenvalue, and H is my Hamiltonian matrix. Work is array, it is a temporary array which will be used by the subroutine which we will be using to now diagonalize our matrix. So, this is this DSYEV. Then we have some also some real numbers, and so x is just my position in space, which corresponds to this value, this x here in my potential. You remember my potential is a function of x. So, it is that x. Dx is the grid I am using to, the size of my grid I am using to discretize this x. norm stores the norm of my wave function, because if you remember, I mean, all the wave functions should be normalized. So, the value of norm should be 1 if my wave function is properly normalized, and then prob this variable stores the probability. So, that means the psi star psi part, and this complex function here f gives me the wave functions, and then I have some integers here. So, where L work and info, these two are again some temporary integers which will be used by this subroutine DSYEV. Okay, so now what do we need as input data? So, for my input data, we need a couple of things. We need to know the depth of my potential well, the user has to provide that, the width of my potential V0, the periodicity of my plane wave which is given by A, and the n, that is which will determine the number of plane waves that is used. So, the same thing is read in this part of the code. So, what this part says is, first it provides a write statement on the standard display, where it asks the user to provide the parameters for the potential well, which is V0 and B. So, once the user provides that information, this is read in by the code. Then you remember by, so we are talking here about an attractive potential. So, the way we are defining the potential in the problem, so that is minus V0, that implies that the value of V0 should always be positive. So, here in this line, what the code does is that it checks whether the value of V0 is positive. Also, my potential has a finite width which is determined by B. So, it checks whether the value of B is greater than whether the value of B is less than 0 or whether it is negative. So, if these two conditions, any of these two conditions are satisfied, the code will stop here, printing the message that my input parameters are wrong. So, this is just to sort of give you I mean to put in checks so that if the user by mistake gives some wrong input parameters, the code can immediately identify that. And once it has read in the values of V0 and B, and then it has done the checking that everything is fine, then for the reference of the user, what it does is it prints out the values. Okay. So, once so this part goes reading in the parameters related to my potential, then we also need to read in the parameters for my related to my plane waves. So, we need to, as I mentioned, we need two things. One is the periodicity of the plane wave, which is given by A, and also we need to determine the number of plane waves that goes into my expansion, which it depends on the value of n. So, that is what the code reads in here. So, it reads in, so this line it asks the again the user to give these values of A and n. Then in this particular line it reads in that values. Then again in the like in the case of the parameters for the potential, here it checks whether the parameters are wrong. So, one thing we need to know need to be careful about is, since we are using plane waves and it has a periodicity of its own which is determined by A. So, the potential for which we are actually doing the calculations, so those are periodic potentials. So, that is if I move from say x equals to 0 to x equals to plus A or x equals to minus A, then what we will have is we will have the same image or the replica of the potential. But the actual potential which we are solving is it is a very localized and just a single potential well. So, what it means is that my A value should be at least greater than B, and in reality the value of A should be large enough, so that the periodic images of my potential do not interact with each other. Also, in the number of this value of n, this should also be always positive and greater than 0, because the minimum number of plane waves you need is at least one plane wave to expand your wave functions. And then once it is satisfied, it has read in these values of A and n, and it's satisfied that it is all the users have given the correct values, it then prints out the values which it has read in for the user to check whether it has read in the values correctly. So, once that is done, then it sets the number of plane waves. So, as I mentioned before, the number of plane waves is twice n plus 1. So, once the number of plane waves is set, then we can start allocating the arrays dimensions corresponding to this allocatable arrays, which I have in the declaration. So, the first array this Kn, as I said, that stores in the k vector corresponding to each plane wave, and its dimension should be the number of plane wave. Similarly, the dimension of my matrix, which is given by H here, the Hamiltonian matrix, that depends on the number of plane waves that goes into the calculations. So, my matrix will be NPW cross NPW matrix, and that is why it has been assigned this value, and it is a 2-dimensional matrix. Then the energy eigenvalues are stored in this array E, and the number of energy eigenvalues will again be the same as the number of plane waves. And then in work it is again a temporary array which is used by the subroutine for diagonalization, where it creates this NPW, it is 3 times the NPW, the dimension of my matrix, which I need to diagonalize. So, once I am done with allocating these arrays. So, what I do now is I start assigning the values of the array. So, to start off with, I need to first define the k vectors corresponding to the each plane wave, and once I have done that, then I need to construct my H matrix. So, this part of the code, what it does is it basically assigns the values of Kn. So, now remember we had discussed this, that Kn can take values of this form. I mean, the n values corresponds to 0, plus minus 1, plus minus 2, and so on and so forth. So, this is of the form of e to the power I k dot r. So, here the Kn first, here we have as the k vector we have assigned as 0 here, the first element of this array as 0, and then what we have done is in this using this do loop, we are assigning the other elements. So, my k vector is basically what I am doing is for the positive one. So, my I goes from 2 to n number of plane waves minus 1, and I am changing it, the do loop is increased by 2 at each iteration. The reason I start from 2 is because Kn 1 has already been assigned here. So, then what I do here is in the first one. So, for example, if my I equals to 2, so this will be k 2. So, this will be this value will be 1, I by 2 will be 1, and then twice pi by a. So, that will be the value of k, and then since in the next line I have I already I plus 1. So, and I am still at I equals to 2. So, this will be Kn 3, and Kn 3 corresponds to minus 1. And that is what I am doing. So, I equals to 2 will give me minus 1 and then twice pi by a. In this fashion, so when I go to the next value, so when I go to the next value, and remember, since the increment is by 2, so the next value of I will be 4. And so, in that way I can build all the other k vectors and build up this complete array. Now, once this is done, so then I start constructing my H matrix. So, before starting to construct the H matrix, what I do is I first initialize my matrix to 0, and then I use this do loop to construct the same thing. So, the size, since the size of the matrix goes from it's an NPW cross NPW matrix, that is the number of plane waves, NPW is the number of plane waves. So, the do loop goes from I equals to 1 to NPW, and the second do loop also goes from j equals to 1 PW. Now, if you remember, so we had two parts in our Hamiltonian, the kinetic energy part and the potential energy part. So, as we saw in the lectures, that the kinetic energy part or the matrix corresponding to the kinetic energy is always a diagonal matrix, and the matrix corresponding to the potential energy, this can have both diagonal and off diagonal terms, while the off diagonal terms is independent of the value of k, the diagonal terms are dependent on the value of k. So, that is why the matrix is the H matrix is constructed in the following fashion. So, first I check whether I am doing the calculations for the diagonal elements. So, what that means is, if I am doing the calculation for the diagonal element, the value of I and j will be same. So, if the value of I and j will be same, then I assign those matrix elements with the values of the kinetic energy, which is k square in my case, and then also the diagonal component of my potential. And if it is off diagonal element, I do not have the kinetic energy, and I assign it only the values of the corresponding to the off diagonal element of my potential. So, once it is done, I am assigning with the matrix, then what I do is I call this subroutine DSYEV and provide this following informations. So, what I provide to the subroutine is the number of plane waves, my H matrix, and this L work matrix. The subroutine, what it returns to me is this energy eigenvalues, which is stored in this E matrix, and also the energy eigenvectors, which it stores in the H matrix again. So, H is a type of an intent out type of variable. So, we will very soon see what this means, what this different the attributes, what this different inputs one needs to provide means. Okay, but before I think before we go to the remaining part of the code, let us just take a look at this particular subroutine. So, if you open the subroutine, you will find something like this. So, it contains all the information, and so the name of the subroutine is this one, and these are the arguments of the subroutine. And if you go down, it also tells what is the purpose of the subroutine, and then what the different arguments means. So, the first argument of this subroutine, that is defined by job z, which when we are calling it in the program here in my program, this particular argument here. So, this is input type of argument, or job z is the input variable which has of character, and it can character type, and it can take two values here. So, one, it can tell the subroutine to either compute the eigenvalues only, or it can tell the subroutine to compute the both the eigenvalues and the eigenvectors. So, remember the eigenvectors will be the information the eigenvector contains in our case when we are diagonalizing my Hamiltonian matrix is the coefficients of which we have used for our expansion of the wave function in the plane wave basis. Since we are not only interested in the eigenvalues, but we are also interested in how the wave function looks like. So, therefore, in the main program we have chose the value to be V here, because we want the code or the subroutine to not only provide us with the diagonalize the matrix, and not only provide us with the eigenvalues, but also with the eigenvectors. Then this is again an input which we need to provide, and that you can tells us which part of the matrix which we are diagonalizing. Here this is denoted by A is stored, whether it is the upper triangle or the lower triangle is stored. And the reason this is provided to the code is because this matrix is a symmetry, it is a symmetric matrix, and when doing the diagonalization, the subroutine exploits the symmetry of the matrix. Then n here is again an integer which is of input type, which contains the information about the order of the matrix, and which is given by this variable NPW here, which is same as the number of plane waves. Then A contains the matrix which we need to diagonalize, which here in my main program here, if you look at it, it's the H matrix. Then there are some other internal parameters. So, basically we need to provide the information about the leading dimension of the array, which in our case is same as the order of the array, which is NPW here. Then the next variable here is this W, which is an output type, which corresponds to this array in my program, the array E, where the eigenvalues will be stored, and the subroutine will return this to the main program. That is why it is an output type. Then LWork is some temporary array, and then info is again an integer and of an output type. So, through this info the code conveys the following message. If the value of the info is equal to 0, then what it means is that it has successfully diagonalized the matrix. If it is less than 0, that is, if it returns a negative number, so what it means is that suppose it returns -5. Okay. So, what it mean is that the fifth argument had an illegal value. Similarly, if it is greater than 0, so what it means is that the algorithm failed to converge the off diagonal element. So, remember in this we do not explicitly diagonalize the full matrix. So, the matrix diagonalization is done in an iterative way, though in this part of the course we will not go into the details of how this subroutine works and how the matrix diagonalization is done, but this is just for your knowledge. So, so now back to my main program. Once I have called this subroutine, it has done its job, then and it has returned the values, that is the eigenvectors which is stored in H and the eigenvalues E and the status that is stored in info. Then I check, then the code, what the code does, it's check first what the status is. So, if it is not, info is not equal to 0, then the code stops here, saying that there is some issue with the matrix diagonalization and it has failed. So, if this condition is not satisfied, the code goes to the next line and it prints out the 3 lowest eigenvalue. Here I have printed out only the 3 lowest eigenvalue, you can print out even more if you want. And then what it does is, it writes the output file, writes to the output file the lowest energy eigenstate. So, remember the matrix, this array here, the array A, which corresponds to in my main code this array variable H, in this subroutine this is an input output type of array. Okay. So, what it means is that through A I supply the Hamiltonian matrix which I, or the matrix which I want to diagonalize, and then once the diagonalization is done, the code returns the eigenvectors through this matrix A. So, each column of this matrix A on returning to the main program gives me one eigenvector. So, for example, the first column corresponds to the eigenvector corresponding to the first eigenvalue, and since the eigenvalues are written in an increasing order of value. So, what in my case, in our case here, when I come back to my main program, what it means is that the first column of this particular array H, which is returned by this subroutine, contains the eigenvector corresponding to my ground state. And so, what I am doing is, now what does it mean that it contains the eigenvectors of my ground state? So, what it means for my case or for our case here is that it contains the, if the coefficients of my plane wave expansion of my wave function. So, using these coefficients, what I want to do is, I want to build my wave function, the ground state wave function here. So, this is how it is done in this code. So, I first open a file which with this particular file name gs-wfc.out, with this particular file name, where this wave function is will be stored in this file, and this I am giving a name, unit name 7. Now, what I do is so my x here, the value of x, so my wave function is a function of x. So, I need to discretize this x here. So, I take dx to be 0.01, and then what I do is, so from minus a by 2 to plus a by 2, remember a is the periodicity of my plane wave. So, I find out how many grid points will be there if each size of each grid is determined by this value of dx, and that is stored in the in this NR. So, this I do just for the half of the part. So, that is why it is a by 2. Then by symmetry, so this the other half will also have the same number of grids. Then norm is the variable where I store the norm of the function, and I compute and store the norm of the function. So, I initialize that first to 0, and then I start building my wave functions here. So, using this do loop. So, since I want to build from minus a to plus a, so that is why it goes from, the counter of the do loop goes from minus nr to plus nr. Once then the next step, what it does is, it computes the value of x, which is the product of this dx into I, the value of the counter of the do loop. Then it sets the f, where it stores the wave functions to 0, and then in this inner do loop which I have here, it builds up the wave functions. So, if you remember, my wave function is like C1 psi 1 plus C2 psi 2 C3 psi 3, where C1 is the coefficient and psi 1 is a given particular plane wave. Say suppose it corresponds to k equals to 0. Okay. Then C2 will be the another coefficient corresponding to k corresponds to the value of n equals to +1. Then C3 will be for -1, and so on and so forth. And so that is what it is done. So this the coefficients of this expansion are read from this matrix H, whose from the first column of this matrix. So that is why the J is the number of rows here, and that is equal to the number of plane waves, because we have same number of coefficients as the number of plane waves. And then so this coefficient you need to multiply it with the plane wave here. So the plane wave is my exponential e to the power I k dot r, and in this case it is k x divided by root a. So this is what the plane wave is. So this is for a particular plane wave, and then to construct the full wave function, what we need to do is we need to add up this for all the plane waves. So that is why we have a do loop here. So once this is done, then for that particular value of x, I know what is the value of my wave function, and once I know that, then I can compute the probability at that particular value of x, which corresponds to my real part of the wave function into the complex conjugate of the wave function. Now, once I know the probability, so this probability then if I multiply by x and I integrate it, that is I add up over all the values of x, that is from minus that is for the complete do loop here, then the value that I get at the end of the day when it is stored in norm is basically my norm of the wave function. And then in this line what I do is I write down my the value of x, the corresponding value of probability at that value of x, and the corresponding value of the wave function. And then since I am interested to check whether it is properly normalized or not, I also write down print out the value of the norm. So once this is done, I close this file and then I deallocate the array, and then I have here a go to statement, because I would like to play around with different values. So go to here is basically brings you to this particular part of the code, this one. So you can rerun the code again by changing the parameters related to the plane waves, that is the periodicity of my plane waves and the number of plane waves. So this is the code, and then let us see how one can run it.